this lecture I will solve few problems in the PN junction under equilibrium condition. So before that I will revise what are the formulas we have derived so far in this PN junction. The first one is the built-in potential V0, which is equal to Vt ln Na Nd by Ni square, right? And the whole concentration in P side is equal to whole concentration in N side into e power V0 by Vt. Similarly, electron concentration in N side is equal to electron concentration in P side into e power V0 by Vt, right? Then the penetration into the N side by penetration to the P side is equal to acceptor concentration by the donor concentration, and the total depletion layer width is equal to xn0 plus xp0. And what is xn0 in terms of the total depletion layer width and the donor and acceptor concentration is W into Na by Na plus Nd. xp0 is equal to W into Nd by Na plus Nd. And we have derived the total depletion layer width is equal to square root of 2 epsilon by q into V0 into 1 by Na plus 1 by Nd, right? Next we have seen the charge densities in the PN junction, that is N side it is equal to q times of Nd, so rho is charge density. In P side minus q times of Na, so Nd is the donor concentration, Na is the acceptor concentration. If we ask what is the net positive charge in N side is, so q times of Nd into the cross sectional area into xn0, that is penetration to the N side. So in P side q minus, that is negative charge, net negative charge is equal to minus q times of Na into A into xp0. xp0 is the penetration into the P side. Then the electric field distribution, to find the electric field distribution from the Poisson's equation, d epsilon by dx is equal to rho by epsilon. So this epsilon is electric field, this epsilon is the permittivity, right? So from this at N side we can say q by epsilon into Nd, in P side minus q by epsilon into Na, right? And what is the maximum electric field is epsilon naught is equal to minus q times of epsilon into Nd into xn0, which is also equal to minus q by epsilon into Na into xp0. And how the distributions of this charge density and electric field distribution will be like this. So in PN junction, suppose P side negative charge, N side positive charge. So the charge density is positive in N side and it is negative in P side. So when we integrate the charge density, we will get the electric field distribution. So when we integrate the negative side, we will get negative slope. When we integrate the positive side, we will get positive slope. Similarly, for NP junction, suppose left side, suppose N type semiconductor is there, right side P type semiconductor. So how the charge distribution and electric field distribution will be like this, because in N side the net positive charge will be there and P side net negative charge will be there. So just it will be opposite. So see here, to represent this positive, net positive charge, or we can say net charge density, right, positive. So there is a positive side rectangular, and in P side negative side rectangle, right? Now when we integrate this, so we'll get positive slope in N side, negative slope in P side, right? So this is the charge distributions and electric field distributions in PN junction and NP junction, right? So these are some formulas in PN junction under equilibrium. Now we will solve numericals based on these formulas. The first one is something like this, very simple one. An abrupt silicon PN junction has Na is equal to 10 to the power 18 centimeter power minus 3 on one side, and Nd is equal to 5 into 10 to the power 15 centimeter power minus 3 on the other. Determine the contact potential V0 at room temperature. Now simple, what is the formula? V0 is equal to Vt ln Na Nd by Ni square. Na Nd is given, so we have to know what is Ni. So in the question he mentioned silicon PN junction. So for a silicon the intrinsic carrier concentration is equal to 1.5 into 10 to the power 10 centimeter power minus 3, and we should know what is Vt. So in the question he mentioned room temperature. So at room temperature, that is 300 degree Kelvin, the thermal voltage Vt is equal to, we can take 26 millivolts or 0.0259, right? Sometimes in the gate exam they will give 25 millivolts also. Now simple, so 26 milli into ln Na 10 to the power 18 into Nd 5 into 10 to the power 15 by 1.5 into 10 to the power 10 whole square. So 1.5 square means 2.25 into 10 to the power 10 square means 20. So this will become 26 milli ln. So 5 by 2.25 into this is 10 to the power 33 by 20 means 10 to the power 13. So when we solve this one, so V0 will be approximately 799 millivolts. So this is the contact potential or built-in potential for these values. Next, I'll solve this question. An abrupt silicon PN junction has Na 10 to the power 18, Nd 5 into 10 to the power 15 centimeter per minus 3, and it has cross-section area of 7.85 into 10 to the power minus 7 centimeter square. Calculate Xn0, Xp0, Q plus and epsilon naught, that is electric field at and we can say maximum electric field for this junction at equilibrium 300 degree Kelvin. Sketch E of x, that is, or epsilon of x, electric field distribution and charge density distribution, right? So Na and D are same what we have seen in the previous example or question. So we can take directly V0 is equal to 799 millivolts because V0 is equal to Vt ln Na Nd by Ni square. So all are same because silicon junction and Na and D are the same as the previous question, right? So this is the question I solved. So same Na and Nd, so we got 799 millivolts, right? So once we know V0, so first we have to find Xn0, Xp0. So what are the formulas for Xn0? Xn0 is equal to W, depletion layer width, into this is N here, so we'll get acceptor concentration by Na plus Nd. So Na either capital A or small a, no problem. And Xp0 is W into Nd by Na plus Nd. So to know this Xn0 and Xp0, we have to find the total depletion area with W. So W formula 2 epsilon by Q into V0 into 1 by Na plus 1 by Nd, right? So 2 into what is epsilon? Epsilon naught into epsilon r. So first we have to find the epsilon naught, which is 8.85 into 10 to the power minus 14 farad per centimeter. Epsilon r, that is relative dielectric constant for silicon, I have given as 12, right? If you see the previous lecture, I have given epsilon naught and epsilon r for silicon. So 2 into 8.85 into 10 to the power minus 14 into 12 by Q. What is the Q? 1.6 into 10 to the power minus 19 into V0, 799 millivolts, that is 10 to the power minus 3 into 1 by Na. Na is given as 10 to the power 18 plus 1 by 10 to the power 15 into 5. So 5 into 10 to the power 15, right? So see, when we are solving the electronic devices problems in the gate, so we have to first simplify the powers, right? So we cannot put directly these powers in the virtual calculator. So this is square root of 2 into 8.85 into 12 by 1.6. Here 10 to the power minus 14, here 10 to the power minus 19. So minus 14 minus 19 means we will get 10 to the power minus 5. If it is going up, this will become 10 to the power 5. So here 10 to the power minus 3 is there. So minus 3 and here plus 3 will be gone. So we will get 10 square here directly into 799. And in the down, if I take 10 to the power 15 common, so this will become 1 by 10 cube plus 1 by 5. So again this will become 2 into 8.85 into 1200 into 799 by 10 to the power 15. So this is 1 by 5 means 0.2. So 0.2, this is 001. So 001. So 0.201. Okay, because 0.001 plus 0.2. So 0.201. So when this will become as 51.65 microcentimeter. This is the total width W. So when we convert into meters, this will become, so 51.65 into 10 to the power minus 6 into 10 to the power minus 2 meters, because 1 centimeter is 10 to the power minus 2 meters, right? So 10 to the power minus 2 is there, so it will become 0.5165 micrometer. This is the total depletion layer width. So once we know the total depletion layer width, so we have to find xn naught, xp naught. So what is xn naught? Xn naught is equal to W, that is 0.5165 micrometer into Na. Na is given as 10 to the power 18 by Na plus Nd. So 10 to the power 18 plus 5 into 10 to the power 15, right? So this will become 0.5165 micrometer into, if I take 10 to the power 15 common, this will be cancelled, so 10 cube by 10 cube plus 1, so this will come out as 0.51559 micrometer. This is the xn naught. So very small change will be there, see, because this is 1000 by 1000 not 1, right? So we'll get 0.5159 micrometer. Similarly, xp naught is 0.5165 micrometer into Nd. Nd is given 5 into 10 to the power 15 by total again 10 to the power 18 plus 5 into 10 to the power 15. So this will be very small actually, so 0.5165 micro. If I take 10 to the power 15 common, this will become 5 by, this is 1000 plus 5, so 1005. This will come out as very small, that is 0.002569 micrometer, or we can say, so when we multiply with 1000, so this will become 2.569 into 10 to the power minus 3 micrometer. This is the xp naught. Now there is a reason why xp naught is very small and xn naught is very large. See, in the question, Na is 10 to the power 18, Nd is 5 into 10 to the power 15. So Nd is very small compared to Na. So that means the penetration into the N side, that is, see, Nd is very small, so penetration into the N side will be large compared to the penetration into the P side. So that's why this variation. So when we add these two, we will get 0.5165 micrometer, right? Next we have to find Q plus and this epsilon naught. So what is Q plus? The net positive charge in N side, right? So what is the formula? Q plus is equal to Q into the donor concentration into the cross section area into x n naught, penetration into the N side. So what is Q? 1.6 into 10 to the power minus 19. Nd is given as 5 into 10 to the power 15 centimeter power minus 3, and cross section area is 7.85 into 10 to the power minus 7 into xn naught. What we got? 0.5159 micrometer. So micro means 10 to the power minus 6 into meters. See, Nd and xn, area is in centimeters, so xn naught also should be in centimeters. So this will become, so meter means, so 100 centimeter, right? Then so 1.6 into 5 into 7.85 into 0.5159 into, this is 10 to the power 15, this is minus 19 means we'll get minus 4, minus 4, minus 7, minus 11, this is 6, minus 17 into 100 means we'll get 10 to the power minus 15. So when I multiply all these values, I will get 32.39 into 10 to the power minus 15 coulombs, right? This is the net positive charge. Next we have to find the epsilon naught. So what is the formula? Epsilon naught is equal to minus Q by epsilon into Nd into xn naught, or minus Q by epsilon into Na into xp naught. So any values we can use. So minus Q 1.6 into 10 to the power minus 19 by, this is epsilon naught into epsilon r, so 12 into 8.85 into 10 to the power minus 14 farad per centimeter into Nd. Nd is given 5 into 10 to the power 15, xn naught 0.5159 into 10 to the power minus 6 into 100 again. So should not be in meters, we have to convert it into centimeters because Nd is in centimeters, this one, right? So this will become minus 1.6 into 5 into 0.5159 by 12 into 8.85. 10 to the power minus 14, this will be, so you will get minus 5. So here, see here, 15 plus 2, so 10 to the power 17 into 10 to the power minus 6, 5, so 11. So this will be 10 to the power 6, right? So when I solve this one, so this epsilon naught is equal to 0.0388 into 10 to the power 6 volt per centimeter. So if I multiply with 100, so it will be 3.88. so I forgot negative sign is there, minus 3.8 into 10 to the power 4 volt per centimeter. This is the maximum electric field in the junction. Now what we need to do, so we have to sketch the electric field distribution and the charge density. So for that, so we have to take again the values W, Xn naught, Xp naught, Q plus and this epsilon naught. So charge density rho is equal to Q times of Nd in N side minus Q times of Na in P side. So what is Q? 1.6 into 10 to the power minus 19. Nd is 5 into 10 to the power 15 per centimeter cube. This is minus 1.6 into 10 to the power minus 19 into 10 to the power 18. So which one is higher? This one or this one? This one is higher, this one is smaller compared to this one. So this is with respect to distance micrometer. This is the charge density rho. If I say Xn naught is very large, so this is somewhere Xn naught, which is 0.5159 micro, and Xp naught is very small, minus Xp naught, which is 2.569 10 to the power minus 3 micrometers, very small. But Q into Nd is small, so that's why the rectangular will be like this, and this Q into Na is very large compared to this one, so it will be something like this. So this is minus Q times of Na, this is Q times of Nd. So this is the charge distribution. This is 1.6 into 10 to the power, we can take like this, 8 into 10 to the power minus 4 when I multiply this. So when I multiply these two, what I will get? Minus 1.6 into 10 to the power minus 1. See, this is 10 to the power minus 4, this is 10 to the power minus 1. This one is large. Next, we have to integrate this charge density, then we will get the electric field distribution. So when I integrate this one, so this is something like this we will get, right? Then this one is very steep, the positive slope, this is the negative slope, this is the positive slope. Minus Xp naught, Xn naught. What is the maximum value? Minus 3.88 into 10 to the power 4 volt per centimeter. This is the electric field distribution and this is the charge density distribution, right? Next I will solve this problem. An abrupt silicon PN junction has Na 10 to the power 17, Nd 10 to the power 16 centimeter power minus 3. This is on P side, this is on N side. So what we need to find? At 300 degree Kelvin, find V naught. So simple, V naught is Vt ln Na Nd by Ni square. This is 26 milli ln Na 10 to the power 17 into Nd 10 to the power 16 by Ni. So what is Ni? Silicon means 1.5 whole square means 2.25 into 10 to the power 10 whole square means 10 to the power 20. So what will get? 26 milli ln 10 to the power 33 by 10 to the power 20 means 10 to the power 13 by 2.25. So this will come out as 757 millivolts. This is the V naught, right? So next one more problem. Boron is implanted into an N-type silicon sample which is having Nd 10 to the power 16 per centimeter cube, forming an abrupt junction of square cross section with area 2 into 10 to the power minus 3 centimeter square. Assume that the acceptor concentration in the p-type region is Na 4 into 10 to the power 18 per centimeter cube. Calculate V naught, Xn naught, Xp naught, Q plus and capital E naught, that is maximum electric field for this junction at equilibrium. So same question. So first we need to find V naught, which is 26 milli ln Na 4 into 10 to the power 18 into Nd 10 to the power 16 by 1.5 square 2.25 into 10 to the power 20. So this will come out as 853 millivolts. You can verify, or simply 0.853 volts. This is the V naught. Next, what we need to find? Xn naught, Xp naught. To find Xn naught and Xp naught, first we have to find the W, which is 2 epsilon V naught by Q 1 by Na plus 1 by Nd. So square root of 2 into 12 into 8.85 into 10 to the power minus 14 farad per centimeter by Q 1.6 into 10 to the power minus 19 into V naught 0.853 1 by Na 4 into 10 to the power 18 plus 1 by Nd 10 to the power 16, right? So when we solve this one, so we'll get 32.71 micro centimeter. This is the W. So keep it in centimeters only because all the values are given in centimeters. So once we know W, next we have to find the Xn naught, Xp naught. What is Xn naught? W into N. This is N. So we'll get acceptor concentration by the Na plus Nd. What is W? 32.71 micro centimeter into Na is 4 into 10 to the power 18 by Na plus Nd. 4 into 10 to the power 18 plus 10 to the power 16, right? So this will be, see, if I take 10 to the power 16 out, so 32.71 micro centimeter into, if I take 10 to the power 16 out, so 16 will be cancelled. This will become 400 by 400 plus 1. So 400 by 401 will get 32.63 micro centimeter. This is the Xn naught. Similarly, Xp naught, so no need to using this formula, that is W into Nd by Na plus Nd. So this is W minus Xn naught, right? So 32.71 micro centimeter minus 32.63 micro centimeter. So this will be 0.082 micro centimeter. So very small Xp naught. Why Xp naught is very small? Very simple. The acceptor concentration is very large compared to the donor concentration. So the penetration to the N side will be more compared to the P side, right? So once we know Xn naught, Xp naught, what is the next one? We have to find Q plus. What is this? Q into Nd into A into Xn naught, right? So what is this? 1.6 into 10 to the power minus 19 into Nd. Nd is 10 to the power 16 is given. Area 2 into 10 to the power minus 3. Xn naught we got 32.63 micro, means 10 to the power minus 6. So this will be 3.2 into 32.63 into, see, minus 19 minus 3 minus 22 minus 6 minus 28 plus 16. So what we will get? 10 to the power minus 12, right? So that 3.2 into 32.6. So this will be 104.41 into 10 to the power minus 12 coulombs, or 1.04 into 10 to the power minus 10 coulombs. This is the Q plus, right? So just now using the calci we can easily multiply these values. Next one, what we need to find? The electric field, that is epsilon naught. What is the formula? Minus Q by epsilon into Nd into Xn naught, or minus Q by epsilon into Na into Xp naught. So here I will use this expression. So we'll see what is the value we'll get. Minus 1.6 into 10 to the power minus 19 by 12 into 8.85 into 10 to the power minus 14. What is this? This is epsilon r, this is epsilon naught into Na 10 to the power 18 into 4. So 4 into 10 to the power 18 is given, into Xp naught, that is 0.082 micro centimeter. So that is 10 to the power minus 6. So this will be, see, 1.6 into 4 into 0.082 by 12 into 8.85 minus 19 minus 14. So this is 10 to the power minus 5, this is minus 6, 10 to the power minus 11 into 10 to the power 18. So minus 1.6 into 4 into 0.082 by 12 into 8.85 into 10 to the power, this is, we will get 10 to the power 7, right? So this value come out as minus 0.00494 into 10 to the power 7 volt per centimeter. This is the epsilon naught. So if I multiply with 1000, what I will get? Minus 4.94 into 10 to the power 4 volt per centimeter. If I take one more, so we'll get minus 49.4 kilovolt per centimeter, right? So this is the electric field in the junction, right? So this is about these 4 problems. In the next lecture, I will solve the gate problems based on this PN junction.